Next, let's analyze another process in which the input signal changes from high level to low level at t equals 0. For the convenience of analysis, the time axis is changed, which is different from the previous page. Similarly, we need to draw the corresponding equivalent circuit before switching. Let's see, before switching, the input is high level, so there is a small resistor R on between D and S of the first stage inverter. Because RL is far larger than R-on, the divided voltage on R-on is very small, approximating to 0, which makes the input of the second stage inverter low level. So there's an open circuit between D and S of the second stage inverter, and the output of the second stage inverter is high level, which realizes function of the buffer. Now we'll analyze the circuit when the input changes from high level to low level at t equals 0. That is, the input becomes short circuit immediately. Similar to previous lecture, we suppose UGS1 changes to low level immediately after the input is a short circuit, which means R-on becomes open circuit immediately. In this condition, will UO1 change to high voltage immediately to form R-on between D and S immediately, and then UO2 changes to low level immediately? The existence of CGS2 makes this part its first circuit, so we need to analyze this time domain process. This is its equivalent circuit. We can also use three elements method to analyze it. You can see that the input is high level before switching, and here is R-on. UCGS2 is divided voltage of US on R-on. So there's a low level approximating to 0. Then UCGS2 0 plus equals UCGS2 equal 0 minus approximating to 0. Obviously, UCGS2 infinite equals US. Tau equals CGS2 times RL. By comparing the previous tau, which is equals CGS2 times R-on parallel to RL, we can find that this is far less than this value. By applying three elements method, we get the time domain expression of UGS2, which is US times 1 minus e to the power minus t over tau. It means that UGS2 increases from 0 to US with negative exponent. When UGS2 increases to be greater than some value, UO2 becomes low level. By comparing these two tau of different time period, we find that the process of input changing from high level to low level is slow, and the process of input changing from low level to high level is fast. This explains the difference of the two change in the simulation. The existence of parasitic capacitor makes that the output of the buffer cannot follow the input immediately, resulting in the transfer delay of the digital system. Parasitic capacitor is the most important factor in limiting the fast development of digital system. Besides the parasitic capacitor CGS in MOSFET, because of the insulation between two parallel conducting lines, positive and negative charges accumulate on both sides respectively, and thus form the voltage difference and parasitic capacitor. According to the discussion in lecture 46, the value of the parasitic capacitor is inversely proportional to the distance between the two lines, which means the smaller the distance, the larger the parasitic capacitance is. This is a great challenge to microelectronics. The important goal of studying microelectronics is to transfer information faster and faster with smaller and smaller size. Smaller size means smaller distance between two lines. But in this condition, the effect of the parasitic capacitor is more and more remarkable. In order to alleviate the contradiction, people have come up with a lot of techniques. You can consult the teaching material of microelectronics for detailed information. Well, this is the end of this lecture.